Okay, so the last time we left off, we were talking about proteins. We're going to transition and start to talk about carbohydrates. We're going to look at a couple of key features of carbohydrates. Specifically, we're going to be looking at the structures and names of monosaccharides. We're also going to look at how open chain and ring forms of monosaccharides contribute to their reactivity. We're going to take a little bit of a look at structures and properties of disaccharides. And then we're going to finish off by looking at the biological function of polysaccharides and glycoconjugates. So one of the things that is interesting to think about, especially when it comes to polysaccharides, is the variety of roles that they play. So whether that's in immunology and specifically responses to different types of pathogens, or perhaps in biofilms, so in medicine and chemistry, dentistry and industry. And then if we're thinking about microbial quorum sensing, this ability for a multitude of cells to send and receive signals. And then we also can think about it in terms of cell or tissue surface protection, things like your joints. So one of the features that we think about in terms of polysaccharides specifically is this ability to fight off disease. But really the way that it does that is because it has a lot of diversity, both in terms of the way it can respond. So for example, if I think about the diversity of pathogens, and I think about the number of functional groups that I see on sugars. Well, if I think about an immune system, its response is going to be something where if I have the cell membrane of a white blood cell and I have a cell membrane of a pathogen and they're charged, well, I can essentially create something that negates the charge, and then that would allow that pathogen to be eaten through phagocytosis. Another way that I can actually think about sugars behaving is in terms of microbes. So microbes are unicellular, but they function as colonies. So if I have an anaerobic layer of bacteria on the outside of the cell, I also have an aerobic bacteria. And so I can actually have these biofilms that have a really significant role in terms of the health and well-being of unicellular organisms like bacteria. So let's take a look at these oxidized polyhydroxyalcohols. So where N is the number of carbons that I see. Glycerol is obviously the parent compound, even though glycerol is not recognized as a sugar. And if I want to look at the shortest or simplest form of sugars, that would be glyceraldehyde. These are aldoses. Notice they have an aldehyde functional group that I see here. Right? I also have dihydroxyacetone that has a ketone, right? That R carbonyl R that I see here. Most sugars, most monosaccharides range from 3 to 6 carbons. And we're going to refer to them in terms of triose, tetrose, pentose, and hexose in terms of the number of carbons. Now, just as a quick recap, it's important for us to recognize that sugars have chiral centers. So glyceraldehyde actually has 2 stereoisomers. Remember, stereoisomers are non-superimposable mirror images. And so if I'm looking at a sugar, I'm looking from the carbon that's chiral, that's the farthest away from my carbonyl carbon, and I'm going to designate that as D, right, or L, left, in terms of the presence of that hydroxyl group. So D and L isomers of a sugar are what we refer to as enantiomers. Most of the hexoses that we see in living organisms are D, and some of the simple sugars we will see in the L form, though, such as L-arabinose. Chiral compounds can be drawn using a variety of different perspective formulas, but most sugars are represented using the Fisher projection. So in a Fisher projection, the horizontal bonds are going to be pointing towards you, whereas the vertical bonds are projecting away from you. And again, I think one of the things that's really useful is we use this to be able to show where we're going to see hydrogen bonding, and it helps us to imagine what these molecules look like in 3 dimensions. So for a Fisher projection, my most oxidized carbon is at the top, and then each carbon is a cross. The H and the OH attachments are shown, and it's planar, right? So I don't necessarily see 3 dimensions, but if I imagine that the stereochemistry of each chiral center is indicated, then above and below the bonds are pointing away from me, and the H and the OH are coming out of the plane towards me. So D-glyceraldehyde is equivalent to R-glyceraldehyde, if you're familiar with the designation of R and S. So for aldoses, every carbon is a chiral center. So I have 2 N-2 possible isomers, or N-2 chiral centers. Another perspective formula is shown here, and again, that's using the wedges and dashes, again, to show what is pointing away versus what is pointing out of the page towards me. If I'm thinking about ketoses, every carbon is a chiral center, and that's going to be 2 to the n minus 3 possible isomers, or n minus 3 chiral centers. So there are 3 carbons in D-glyceraldehyde. Notice there are, 4 carbon sugars, 5 carbon sugars, and 6 carbon sugars. If we take a look at these sugars, one of the things we're going to notice is that if there's a difference in configuration at only 1 carbon atom, that's what we're going to refer to as an epimer. So for example, D-mannose has an epimer of D-glucose at the C2 carbon, where I flip-flopped that H and OH. If I looked at D-galactose, it has an epimer at C4 for D-glucose, where again, I flip-flopped those two. So an epimer is different only at 1 carbon position. If we think about this, then we have D-glyceraldehyde, which has those 3 carbons we talked about, and then there are 4 carbon sugars like D-erythrose or D-threose. We have 5 carbon sugars like D-ribose, D-arabinose, D-xylose, and L-xylose. And then we have the famous 6 carbon sugars, the 3 which are circled here, or rather boxed, the D-glucose and D-mannose and D-galactose, are some of the more common sugars that we see. If I'm looking at my D-ketoses, dihydroxyacetone is my 3 carbon D-ketose, whereas D-erythrulose is my 4 carbon, and then I have some 5 carbon ketoses, and I also have 6 carbon ketoses, the most famous of which is probably D-fructose. And it's important for us to think about the fact that these sugars are going to exist in one of 2 forms. They're going to exist either in their straight chain form, which is the linear that we've looked at, or in a ring form, and that's what we're going to look at next. So thanks for listening. We'll catch you next time.